Any questions from yesterday's discussion? Naming ketones, aldehydes, pretty straightforward. So let's think about the mass spectrum of ketones and aldehydes. I told you this acylium ion a few days ago should be familiar from a mass spec. So that's where a ketone can cleave. This is stabilized by resonance. And so here's 1, 2, 3, 4, 2 butone. And so if we imagine cleaving it right there, we'll get this 57. Where's the 43 come from? Probably cleaving it right here. So we get 2 acylium, cleaving it on either side. So for fun and no prizes, why is this peak higher than this peak? Why is 43 the base peak and not 57 the base peak? Absolutely. Think back to your cation stability, and the radical stability follows the same rules. Not a very stable radical, primary radical, a lot more stable. So there's why you get your base peak there at 43. Butyraldehyde, that must be the common name. Butanol would be the IUPAC name. So you've seen this before in the mass spec chapter where we did a structure from a mass spectrum, beta cleavage, beta alpha cleavage, loss of a methyl, loss of 15. That doesn't seem very good. Here's our molecular ion. There's loss of 15. And here's this big thing, 44. And recall that we noticed that most things start out with an even molecular ion and all the fragmentations were odd. And so when you see even things, you get excited, like loss of 18, loss of water with an alcohol that tells you water. Here's this even peak, 44. So what's going on with that? This thing called McLafferty rearrangement. We'll see that on the next slide. When that occurs, you get loss of 28. And I think ethane, loss of 28. And this will happen with anything 4 carbon chain aldehyde or longer. 1, 2, 3, 4. You can almost see a magic perfect 6-membered ring there. And these electrons grab that hydrogen. And you get to that point, and then these electrons jump back on here. And so here's this ethane, the loss of 28. And here's this thing called an enol. I think we'll talk about enols in a little bit. You've seen enols before with the hydration of an alkyne. In the fall, we saw that. The net result of this rearrangement is the breaking of the alpha-beta bond and the transfer of a proton from the gamma to carbon to the oxygen. Alpha, beta, gamma. Love to use those Greek letters. An alkene is formed. So if we had pentane, there'd be a methyl group here. If we had hexane, there would be an ethyl group. So 4 carbon chain and longer, you can get this McLafferty rearrangement of any aldehyde. And back to the enols, this tautomerization of the enol. Does anybody remember the tautomerization of an enol? Where it looks like this proton gets transferred over here. It may not do this in the gas phase. There's the tautomerization. Jog your memory. Electronic transitions. Notice we got a double bond with carbonyl carbon. Propanol. So that's conjugated there. Absorbs at 210 nanometers. And this epsilon thing, that's the molar adsorptivity. So these things strongly absorb in the UV spectrum. And once again, as I said the other day, we don't use UV spectroscopy to determine structures, but we can measure concentrations. So from an analytical chemistry point of view, quantizing what's there and absorbing UV is in a conjugated system is a pi bonding to a pi anti-bonding molecular orbital. And some interesting things we don't care about. Here's the pi bonding to anti-bonding transition. And the allowed transition has a higher molar absorptivity than the forbidden one. Carbonyl carbon absorptions are very weak, and they're often obscured by stronger absorptions. Therefore, they're rarely useful as the pi transitions. So some historical things with aldehydes and ketones. Acetone and methyl ethyl ketone are common industrial solvents. I've seen bottles of this, or cans, at Home Depot. Cans of both these at Home Depot. Formaldehyde is used in polymers like Bakelite and many other polymetric products. I don't think these are used for flavoring. Hopefully you're not flavoring your food with any formaldehyde, but a lot of aldehydes. I'm thinking vanilla, vanillin. Butyraldehyde has a buttery flavor, probably put in margarine. And when butter goes rancid, you get butyric acid, and that's disgusting. Here's the vanillin, acetophenone. I don't know if I like pistachio ice cream as much as I used to. It seems like an awful benzene molecule to be munching down on. Had cinnamon in my oatmeal this morning. Camphor, a ketone. This almost looks like, if I took that away, what would that look like? You isolate it in lab and looked at the NMR of the orange pill oil. And when I look at this carbon here, I see 4 different groups. Here's an asymmetric center, and one isomer tastes like spearmint gum. The other isomer tastes like caraway seeds. When I was a kid, I hated eating the rye bread my parents would procure from the store. Once I became an adult, I've figured out you can buy rye bread that doesn't have caraway seeds in it. Seems like musk cologne for men was big in the 80s. Musky aroma. So in the alcohol chapter, we looked at reacting Grignards with ketones and aldehydes to get tertiary alcohols or secondary alcohols. So this is a familiar thing to you. Here's the Grignard, here's an aldehyde. Think about it. A pair of electrons there in that charge slams into there, those jump up, and then you protonate it. So here's a secondary alcohol. And from the alcohol chapter, we can oxidize a secondary alcohol to a ketone. So here's a source of a ketone. Of course, we had to have an aldehyde to start out with. A Grignard reagent can be used to make an alcohol, and then the alcohol can easily be oxidized. And here's our PCC. It's a toned down chromate. So remember, the sodium dichromate in sulfuric acid doesn't stop at the aldehyde. It goes all the way to the carboxylic acid. So here's cyclohexymethanol and PCP. These are some other reducing agents. We don't really care about them. PCC is the only one you need to know. So here's our cyclohexane carbaldehyde. Pyridium chloral chromate, selectively used to oxidize primary alcohols to aldehyde. Stops at the aldehyde. And this Swern reagent can also be used for an oxidation. And you've seen this before from the alkene chapter, the ozonolysis. When I think about cleaving that and putting a carbonyl carbon right where those are. And then we just had in the alcohol chapter 10, a thioether getting oxidized to a sulfide. Double bond is oxidatively cleaved by ozone, followed by reduction. Ketones and aldehydes can be isolated products under these conditions. So depending on the makeup here, here's a hydrogen, so there's where the aldehyde comes from. Here's where you're going to get the ketone. Fields-Crafts reactions. So we just went over those. Not sure what G stands for. R is alky or aryl. G is hydrogen, an activating group or halogen. So all those are what type of directors. You can look up there and tell me para and ortho directors. So there's the 2 different ketones you'd get. So if G is hydrogen, that's just benzene, and that would be straight up Fields-Crafts acylation that we just went over. So here's an example, connecting this to a benzene ring. Reaction between an acyl halide and an aromatic ring will produce a ketone. All right, now we get to talk about the keto-enol-tautomerism. So this is a review of chapter 9, the alkyne chapter. The mercury and the sulfuric acid gives you a Makarnikov hydration here. This carbon got the hydrogen. It was richer than this one that doesn't have the hydrogen. So the OH goes there. And the enol isn't isolated. It taumerizes into the methyl ketone. Ethyne cyclohexene. Here's the enol. Here's the methyl ketone. So the initial product of a Makarnikov hydration is the enol, which quickly tautomerizes to its keto form. How many of you forgot that from the fall? One honest person. No, most people smiled, so I imagine the smile was a yes. Internal alkenes can be hydrated, but a mixture of ketones. What does that mean? Internal means no hydrogen. Let me just come up with one. Why don't I do this thing here and add a little extra? That ought to be good enough. Same reagents. So an internal alkene, you're going to get the carbonyl carbon on both of those. Not both at the same time, but one and the other. So that would be the mixture. May not be that useful synthetically. Hydroboration oxidation of alkynes. So the one I got real memorized is the BH3 and THF. BH3, THF. And the whole point of that is the anti-Makarnikov hydration of a alkene when we did the alkene chapter. So this is similar. So that's going to put the OH on this group. There it is. And of course, it tautomerizes not into the corresponding ketone, but an aldehyde. Look at that. It's like this hydrogen goes over there and you make the carbonyl carbon right there. So here's a real life example. Normally Makarnikov would say this gets the hydrogen, this gets the OH, then you have a double bond. Tautomerizes into a methyl ketone. That's not going to happen. It's going to put the OH here and a hydrogen there, and they don't show the enol, and it tautomerizes into an aldehyde. Hydroboration oxidation of an alkyne gives an anti-Makarnikov additional water across the triple bond. So kind of a lot of review with the ketone and aldehyde chapter. Synthesis of ketones from carboxylic acids. So a partial positive charge here. It's a nucleophile. Here's an organometallic reagent, phenolithium. You can draw 2 electrons there and put a charge, and you can imagine that slamming into there, those electrons jumping up. And unfortunately, or fortunately, there's this thing called a hydrate. I should have rearranged all the slides. And this hydrate can lose water and form this ketone here. And this is fairly generic. Organolithiums will attack the lithium salt of carboxylic acids. The lithium salt. What does that mean? Notice here's a protic proton. This is a carboxylic acid. The first proton just kills this. I imagine if you wanted to do this synthetically and save on your reagent, you might make a salt of the organic acid to begin with. Or maybe there's a solubility and you have this in like THF or ether. Or the lithiums, you don't have to be in an ether. You could have this in dry benzene or whatever. First, you protonate one of these benzene rings, and then you have the lithium salt, and then the second one slams into there and proceeds. Protonation of the diene forms the hydrate of a ketone, which quickly loses water to give the ketone. Well, here's our Grignard. Ketones from aldehyde and aldehydes from nitriles. So here's a nitrile, very, very similar with partial negative charge, partial positive charge. So nucleophile, electrophile, and then we get the magnesium salt of an amine. We're going to have to learn about amines, amides. So here's the amine. Once this thing gets protonated, And these hydrolyze into a ketone with water. In the next chapter on nitrogen chemistry, we might take a ketone and try and go back to the amine and basically get an amine out of the whole thing. A Grignard or organic lithium reagent can attack the carbon of the nitrile. The amine is then hydrolyzed to form a ketone. So think a lithium aluminum hydride, powerful reducing agent. This is dibutyl aluminum hydride. It's only got one hydride on it. The lithium aluminum hydride, you recall, had the formula LiAlH4. So it's a calm down reducing agent. Here's a nitrile, and notice we've added a hydrogen from the hydride. Then we add some water, and you can think of it putting the oxygen there. So here's an aldehyde. Here's a real life example. Notice it doesn't reduce the double bond. Aluminum hydrides can reduce nitriles to aldehyde. Diisobutyl aluminum hydride, abbreviated IBU2ALH, or this other one commonly used for the reduction of nitriles. Nitriles to aldehydes, aldehydes from acid chloride. Here's the acid chloride. If we can just put a hydrogen there, we'll have an aldehyde, and our reducing agent will do that. Lithium aluminum tributoxyhydride is a milder reducing agent, because before, remember, you hit this with a lithium aluminum hydride, you would get the primary alcohol. Chemists have found ways to calm down the hydride and make it milder so it stops at the aldehyde. Lithium dialkyl cuprate reagents, here it is. And you want to think of all these being the same, 2 electrons, a negative charge. It's going to come slam into here. Probably have a tetrahedral intermediate, have chloride as a leaving group. You can see that hooks up with the lithium in 2 of those. So I don't know what happens with this, but there's our ketone. A lithium dicuprate will transfer one of its alkyl groups to the acid chloride. Seems like you should be able to do some chemistry with that organometallic right there. Grignards and organic lithiums cannot do this reaction. Has to be this copper. So nucleophilic addition. Once again, carbonyl carbon has that little positive charge. Nucleophile hits that. You have an alkoxide. A strong nucleophile attacks the carbonyl carbon, forming an alkoxide ion that is then protonated. And aldehydes are more reactive than ketones. I told you that one of the highlights of this chapter is this thing called a hydrate, and acetals and hemiacetals. And we saw that formaldehyde existed as this thing called formalin, which was the hydrate of formaldehyde. So there's this thing called hydration of ketones and aldehydes. There's a ketone and water adds somehow, and we have this thing called a hydrate. And you remember the terms vicinal and geminal. So this is a geminal diol. You got 2 OHs on the same carbon. And this is a reversible thing. It's under equilibrium conditions. So the equilibrium constant for this thing is going to be the hydrate and the concentration of ketone in water there. So here's acetone and water. Here's acetone hydrate. And you can see not a very large equilibrium constant. So most of the time, things are over on this side. In aqueous solution, a ketone or an aldehyde is in equilibrium with its hydrate, which is a geminal diol. With ketones, the equilibrium favors the unhydrated keto form of the carbonyl carbon. Keto, there's kind of a similarity there. How does the hydrate form? We're going to look at acid catalyzed. So all carbonyl chemistry that's acid catalyzed, the first thing you do is protonate oxygen. And that makes this positive charge more accessible due to resonance forms. So water can run in there as a nucleophile. Water can then pull off this proton. Now we've regenerated the catalyst. Acid catalyzed. Hydronium ions are catalyst. And here is the hydrate. the hydrate of the ketone. Hydration occurs through the nucleophilic addition mechanism with water and acid, or hydroxide and base serving as the nucleophile. So this is the acid catalyzed hydration of a ketone mechanism to get to the hydrate. The base catalyzed seems fairly straightforward. Base runs into carbonyl carbon, protonates that off. We're in an aqueous solution, pull a proton off water, and we've regenerated our catalyst. Doesn't always look like a catalyst. Looks like it's a reactant. Protonation of the intermediate gives the hydrate. All right, wanted to talk about hydrates. We can talk about the Wittig reaction next time we meet.